My name is Daniel Sanchez. I work for Wolfram Research, South America. And today I'm going to talk about Wireworld, which is a 2D cellular automaton. And I'll give you the necessary things, the basic bits, so that you can start to understand other constructs done on top of Wireworld, and maybe even designing your own computer. So yeah, so what is it? It's a 2D cellular automaton suited for simulating logic, digital logic. It was created by Brian Silverman, which should be around lurking here, watching this talk. He was invited around 1984, and it first appeared in the book The Phantom Fish Tank. You see here, this is a chapter in which it was introduced, alongside other things he did. Right. So the basic setup is, instead of having just two cells, black and white, like in the game of life, you have 4 cell states. And these are the 4 cell states. You have a empty or blank space. You have an electron head, an electron tail, and a wire or copper cell. And with that and some smart rules, you can do really cool stuff. And my original objective was to build this, to explain this Wireworld computer that's in the web. You can look for it. This computer will print here the prime numbers, starting with 2, 3, 5, etc. So I wanted to, reverse engineer and try to explain each part of the computer. I won't do it completely because of the time, and because I haven't finished my studying of this, but I'll give you some interesting parts. So the rules are, just like in the game of life, when you want to update a cell, you look at the cell value and its neighborhoods, and this is the more neighborhood. So the 4 rules are: if you are an empty cell, you remain an empty cell, so the background never changes. If you're an electron head, you always turn into an electron tail. If you're an electron tail, you always become a wire cell. And if you're a wire, you might become an electron head if and only if you have one or two electron heads in its neighborhood. Otherwise, it remains a wire cell. So I wrote a couple of years ago this Packlet, which is in the Packlet repo, and I updated it last night with some new stuff. And you can install it and you can play around it if you have the notebook. Every page has a documentation page. One cool thing, which is the one thing that I used the most, was this Wireworld draw, which is, I got inspired by this molecule draw that we have in Mathematica, in which you can draw states, right? If you click, you can cycle through cell states. You can do some nice stuff here, like set which cell you want to drag, etc. And if you shift return, you get the state, and now you can play around with that. Okay, so electrons. I'm going to now talk about, from the ground up, all the things that you might need to do a computer. So electrons are an electron head and a tail, and it's an electron that will propagate in the direction of the electron head at the rate of 1 cell per generation. So we have this basic setup. We have a wire, and at generation 0, we have an electron pointed to the right. So if we evolve this state with the wire rules that I mentioned before, you'll see that this electron head turns into an electron tail. That always happens. This electron tail always turns into a wire cell, and this wire cell will become an electron head because it has just 1 electron head in its surrounding neighborhoods. And if you evolve that for several generations, you have this electron moving to the right? Or you can do an animation like here. Electron turns around corners. If you follow the rules, you will see that there's no problem with corners, so electrons will move around corners. I'm showing just here the function that I wrote, which is evolve and plot, and yeah. So if we have corners, we can have loops. If an electron is inside a loop, it will go around forever. And we can start talking about signals. So we might say that we can divide a wire into segments of equal length and say that if an electron is in the start of the segment, we can say that the signal is on, and if the electron head is not there, it's off. Yeah, so this requires synchronization between the sender and the receiver, so that everything works as you would expect. And there's a choice of the segment. What's the best segment length, right? That changes how we construct things. So if our system works with a fixed set of segments, we call this an N-micron technology. But there are some restrictions for that. So segments must be at least large enough to contain the electron head and the tail, so minimum 2. But practical operations demands at least one empty cell between the electrons, so making 3 the actual minimum. If not, you get this. You have 2 electrons here, and if you start evolving, one of them will disappear. Right. So all necessary computer logic can be implemented in 3-micron technology, but because of simplicity and compactness, we are going to use 6-micron technology, and you'll see why later. But you will still be able to get the 3-micron technology with some frequency doublers. This is another example of a signal. So we had a loop before. What if we attach a wire? If we do that, we see that if the electron head gets to this spot here, at the next generation, the electron will continue to loop in the loop, right? But also an electron will be emitted from the loop. And yeah, this is what I would call an electron emitter. And you will notice here that each electron is separated by 6 cells. Here are some examples of some wires. The top one carrying a continuous stream of zeros, the bottom one a continuous stream of ones, and you notice that we can, divide the electrons. This won't happen in real life, but you can do it here. And the bottom wire, if you look at this cell here, it's carrying 101 indefinitely. So one key observation is that the loop size, there's a correspondence between the loop size and the period of the electrons being emitted. So the observation is that the emission interval is equal to the loop's total length. So this loop has 12 cells. So there's a 12 cell spacing between electron emissions if you count each cell here. That's one of the observations. Another one is that it doesn't matter what the shape of the loop is, as long as it has 12 cells counts in this example, the period is the same. And this also carries a practical limitation, which is why the 3-micron technology is a bit challenging, or at least creating a 3-interval emitter. This is here an example of a 4-interval emitter, but yeah, as I mentioned, we will work with 6-micron technology. So let's start constructing some logic gates. So the diode allows the flow of electrons in only one direction. So here in this example, an electron is coming from the top, and you will see that it's going through the right way of the diode, which is why an electron is moving downwards successfully. But in this example here, the electron is coming from the bottom and it's going the wrong way, so that's why an electron is not being transmitted to the top. The key observation of how this works is that when the electron comes through the wrong way, at some point it will create this 3-electron head state here, which will prevent this wire cell here to convert to an electron head because of the wire rules. So wire cells only convert to electron heads if it's surrounded by 1 or 2 electron heads. In this case, it's 3, so it won't convert to an electron head. And in the right way here, like here, this is designed so that this doesn't matter. So that's why there's a flow if it faces the right way of the diode. And the most fundamental logic component, maybe, I think, it's the OR gate, and it's this example here. And you'll see here that if this is the gate, this cross-shaped 5-wire cell arranged in a cross shape, if there's no electron coming to it, there's no electron coming out. This will become the norm for other gates. At the generation 6, you will see an electron coming in and an electron comes out of the gate. At generation 12, another electron comes in and also comes out. And if both wires, let's call this bottom one A and this B, input the OR gate, you will also see an electron being emitted, just like you would expect. I'm not showing to the left, there's 2 electron emitters, so I'm just focusing on the gate. One subtle but crucial design feature is this ear here, this wire cell here, which prevents the propagation backwards. So if an electron comes from the top or the bottom, if this ear here didn't exist, it would propagate backwards, and it will probably cause interference with other signals coming from the other wire. Yeah. Another important gate is the XOR gate, which is, you can see here. XOR gate is only returns, outputs an electron if either one or if only one of the wire inputs is 1. So if the top one inputs an electron, you will get an electron. If the bottom one inputs an electron, you will get an electron. But if you input both electrons, you won't get an electron. And that's, you can see here the wire rules at hand. And this is the Boolean table that represents this gate. Yet another gate, we can implement, this is one of implementation of the AND NOT gate. So if we call this A and we call this B, this gate here has 2 wires as outputs. One of them is the AND OR B gate, the OR gate, and the other one has the A and NOT B output. So this means that if A or B is 1 or both, this wire will always output an electron, but this wire will only output an electron if A is 1 and B is 0. So let's see that happening. So if B is 1 and A is 0, only 1 electron comes from the bottom. If A is 1 and B is 0, both wires should have an electron. And if A and B are both 1, only the bottom one also has an electron being emitted. So the secret to how this works are these small copper ears. Again, these single extra cells sticking out near the outputs. When an ear is present, this wire calculates the AND NOT gate. Without this ear, like in the bottom part here, this construct calculates the OR gate for this wire. So if we have both ears present, this gate becomes like broken crossover, so it allows exchanging an electron from one wire to the other, right? As long as both electrons are not coming at the same time. So you have to keep that in mind. This is another implementation of the AND NOT gate. It's a simpler one, takes less space, but it only outputs one wire, which is the AND NOT, and you don't get the OR wire, right? And this is an excellent resource. This is what I used for doing this tutorial for the most part. You can look at more stuff from here. Right, so with that, we can now start constructing a ROM. So a ROM is a read-only memory cell, and we have two varieties. If this is, you will see that this is the broken crossover construct. So if there's an ear here, we will say that this ROM cell stores a 0, and if there's no ear here, this ROM stores a 1. Yeah. So how do we use that? So we will send signals from the right, from the southeast, coming from the bottom right, and it will enter this gate. And if there's an ear here, you'll see that an electron won't be outputted from this wire. Why? Because this is the B and not A gate. B is 0. Imagine there was a wire here. And so this means that this will only turn on when B is true, which will never happen. So this will always be 0. And this is the unknown B wire. Given that B is false, this is the A wire. So you will see that an electron will always come from to the right, to the top left. But if there's an ear here, it will never go to the right wire at the top. If there wasn't an ear, an electron will be emitted in this second wire at the top. So that's how if you send a signal, you would, what you will get is either 0 or 1, depending if there's an ear. So you can see that that's how we could read a bit from this construct here. So this is an example of a minimal decoder in which I arranged 6 ROM cells. You will notice that, and the idea is that we have 3 input lines, and with one input line, I want to read the contents of these 2 ROM cells. So if an electron comes from here, it will read, this is a 0 and this is a 1, as we saw before. So I expect that a 0 and 1 electron comes from here. If I send a signal through here, I expect to see a 1 and 0 being emitted to the top 2 wires, and here a 1 and 1 and a 1, right? So this only works if only one signal input line is active at a time. So this is an example of the 1 being the input 1 having an electron, and you will see that I have a 0, 1 at the end here. If I activate the second wire, I'll get a 1, 0. And if I activate the third wire, I get a 1, 1. So basically, this is encoding a number into its binary representation. So we can use that later for our, okay. This is a big thing. Okay, maybe I have to run it. Okay, it's a big ROM, which maybe I want to show now. Okay, next, the flip-flop. Right, so this is a device that can be in either one of 2 states, a set or reset. And you set it by sending an electron through this A wire at the bottom. You see that if I send an electron there, an electron is emitted, but also trapped in this loop, right? And the purpose of the top wire is to send an electron so that it clears this electron being trapped here. So that's how you would reset this flip-flop, right? And the one thing to note is that you have to be careful with the synchronization. So you have to send the top electron at the right time so that it cancels the electron being trapped in the loop. Yeah, this is more stuff. With that, we can implement a binary adder, which I think I don't have much time to explain in detail. But the idea is that if I encode this number 3 here as in its binary representation and lay out the electrons here and the 6 the same, I will get like, so 3 is 0, 1, 1, 6 is 1, 1, 0. If I run this for 48 generations, I think, I will get the output, which is 9, and it's 1, 0, 0, 1 in binary representation. So I want to show how I would use that. This is the state of the Wireworld, which is this without any electrons. I take two numbers to this function. I take the x and y. I convert the x to its binary representations, so 3 is 0, 1, 1, and I lay down the electrons in the state. So I draw these two electrons here. I do the same for 6, and then I run the evolution for 48 generations. And at the end, I look at these positions here, take out the bits, and reconstruct the decimal number. So yeah, I can do the worst binary adder, the most inefficient one, but it outputs the correct thing. 1 is 2, 1 plus 1 is 2, 7 plus 7 is 14. And you can see here the simulation of this. So here I wanted to explain, but I think I won't have much time for this. But you will see familiar constructs like the XOR gate here and here. This is the AND gate, the simple version, like here and here. There's a loop here, a flip-flop here, some delay paths. And you can start, dissecting this and reverse engineering and studying it part by part. So the first part, which corresponds to this, is a half binary adder. And, if you get a 1, 0, the sum will be a 1, 0. Without the sum will be a 1, the carry will be a 0. The same if in vice versa. So a 0 and 1 will also get a 1 and 0, so no carry. And the 1, 1, you will expect to see a sum of 0 here and a carry here. That's what we have. And there's more stuff later so that we can support a full binary adder. So I think I will leave the questions up until the end because I don't have too much time and I want to show a lot of stuff. I'm going to talk about now the clock system used in the Wireworld computer, which you will see it's at the bottom of the whole computer. We talked about an electron emitter, but if you wanted to have electron emitters with bigger periods, which you will want because, you will need this. The only way now we know how to do this is by making the loop larger. So this is a bit, it becomes space expensive with bigger values. And that's why we have this clock system, which introduces these frequency dividers that will divide the frequency or by vice versa, multiply the period by 2. And it's composed of 2 logic gates, the XOR and the AND NOT gate. There's a loop here, and there's a delay path. So you start with the make clock signal. In this case, is 30. It emits an electron every 36 steps. And then you add this frequency divider, and the idea is that it will emit an electron to the right here every 72 steps instead of 36. So twice the period. So you will see that the first electron being emitted here, it's at generation 17 here. And then also at generation 89. So if you subtract that, it's 72, which is twice the period of the original emitter. Yes, and I'm explaining here in detail. But the important thing is that you have to be really careful with the synchronization of your gates, which is the most important part of constructing this kind of computer in Wireworld. Yes, more. So if I have 2 frequency dividers now, I multiply the original period by 4, so I have a period of 144, and I can keep adding stuff until I get the period that I want. So in the computer, it has outputs for after the 5th and 6th a frequency divider. So it's working with these two frequencies. I want to talk about a bit about the second digit display, which is, I think, the most, it's nice to see some output. And it's composed of seven segment displays. So each of these is a segment. There's a ROM below the display, and there's a ROM controller. So the 7-segment display is arranged so that each segment corresponds to a separate wire path. So if you want a 1, you will turn this segment here and this segment here. And each segment is controlled by an input, which you will see. It's one of these: 1, 2, 3, 4, 5, 6, 7. Each of these inputs turns on one of these loops, of these segments. So we can do that with by trapping electrons, or sending a constant stream of electrons to the segment. This is a loop of length 6, so it follows the 6-micron technology. But we can add a frequency doubler so that it appears, the electrons are closely together, so it appears more bright. I haven't talked about this, but it's simple how it works. So that way we can have, a digit being shown up on this display. I talked about the ROM in a minimal form, and this is a bigger version which has 10 inputs, one corresponding to for the numbers 0 to 9, and it has 7 outputs corresponding to each segment that you want to turn on. So in this case, I'm sending a constant stream of electrons to the second address. So this is the 0th address, this is 1, this is a 0. And you will see that this second address is emitting electrons based on if it has an electron here or not, like we discussed before. And those electrons that are emitted will turn certain segments on the display. That's how you move digits around. In order to supply a constant stream of electrons and to control which address you want to turn on, that's the job of the ROM controller, which is this side of the construct here. So it has a bunch of parts, which I won't go into detail, but you will see that it has 9 outputs corresponding to each number, to each digit. And the important part is that there's this next command that if you send an electron at the right time, it will move from one address to the other. So if I send an electron here and it was only emitting the address 2, the contents of address 2, it will, after some evolution, it will start sending the information contained in address 3. Okay. Yeah, so I think I don't have much time, so I won't finish this. So let's see some examples, right? So this is 0, and when I send a 1 at the right time, you will see that it becomes, after some generations, it will become a 1. Same here, it was a 1 and it becomes a 2. This was a 2 and becomes a 3. There's a register bank. The Wireworld computer has 64 registers actually, and each of them can store a 16-bit number. And there's a way to send a read signal and a write signal. So I haven't fully studied this, so I won't go into detail, but this is a summary here. Sometimes skip later. Yeah, this is the Wireworld computer again. And we can run some some evolutions. And according to my notes, at the 11th K generation, we will see a 2. And then at the 38K generation, we will see a 3, and so on. So all the prime numbers up to 5 digits will be shown here eventually. But yeah, this is a start. Here is the frequency doublers. These are the registers. These are the 7-segment displays. So I've covered a bit, but I haven't covered everything in this computer. So yeah, that's. Let's just wait for the 3. That's all I wanted to talk in this presentation. So if you have questions, I will remain here, or you can contact me. Let's see the 3. Okay, there's a 3. So yeah, there's here I put another example which appeared in Mathworld, and yes, some really useful resources I used. So yeah, you can email me or you can talk to me in community. So that's my presentation, and thanks. Yeah, it also flew a bit over my head at the beginning, but I think having the display and the graphics really helps, makes me understand better what's happening here. Yeah, it has everything: a ROM, state machine, and a loop. Yes, thanks, Sean. I think I like that it's very visual. That's why I played with this.